Welcome back. Let's talk about some new data structures over here. We have stacks and queues. Queues with probably the most confusing spelling of all time. Don't worry, even I, who am fluent in English, have a really difficult time spelling this, but it's queues. Anyway, don't worry, the data structure itself is not as confusing as the spelling of this data structure. We're going to learn two at the same time, stacks and queues, because they're very similar. They are both what we call linear data structures. And linear data structures allow us to traverse, that is, go through data elements sequentially, one by one, in which only one data element can be directly reached. And this will become more clear to you as we talk more about stacks and queues throughout the next couple of videos. Now, the reason that these are very similar is that they can be implemented in similar ways, and the main difference is only how items get removed from this data structure. You see, unlike an array, in stacks and queues, there's no random access operation. You mainly use stacks and queues to run commands like push, peek, pop, all of which deal exclusively with the element at the beginning or the end of the data structure. Now, after I said that, what was your first thought? Does it kind of sound limiting that with stacks and queues, we usually only can access the first or the last element in the data structure? Why would we ever want to use something like this? And this is an important topic in computer science. You will see that we can build things like stacks and queues, which are using arrays or linked lists. Except, unlike arrays and linked lists, we have less methods or less actions that we can perform on stacks and queues. And sometimes it's good to have these higher level data structures that are built on top of lower level ones like linked lists and arrays to limit the operations you can do on them. That's actually a benefit. In computer science, having this limited ability on a data structure is an advantage because you can control that whoever uses this data structure performs only the right operations that are efficient. If you give somebody all the tools in the world, it's a lot harder for them to operate than if you just give them 2 or 3, so that they know exactly what they need to do. Now, let's talk about stacks and queues throughout the next couple of videos to really understand how they work and then finally code our own. I'll see you in the next one. Bye-bye. Let's talk about stacks. Stacks is a type of data structure that, well, you can think of them as plates. That is, we have one piece of data, and then another piece of data comes along and gets stacked on top of that piece of data. And it keeps going, keeps going, keeps going, and keeps going. You can think of it as these plates stacked on top of each other vertically. And you can only touch the top plate. You can't really access anything from the bottom over here. The way you can access data from a stack is to grab the first plate, then the second plate, then the third, and you keep going and you keep going and you keep going until you've gone through all the stack. And this is called LIFO, or last in, first out, because the last item that comes in is the first one that comes out. And you're thinking to yourself, why is this useful? When would we actually use something like a stack? They're actually useful in quite a surprising number of ways. They're very good, obviously, when you need to know the very last value that was seen or added. And stacks are very important in language-specific engines. You might have heard of something called Stack Overflow, a website that a lot of engineers visit. And I'll actually include a bonus video after we talk about queues of how the JavaScript engine works using stacks and queues, and how you might get Stack Overflow when you write bad code. Now, most programming languages are modeled with the stack architecture in mind. And when functions get called in a programming language, usually they follow this model of last in, first out. A function within a function within a function gets called, and then we start popping those functions until we get to the very beginning. And don't worry, this is going to be a little bit more clear when we actually code our own stack. Another useful way that we might use stacks is such as browser history, right? When you go back and forth from one website to another, and then you hit the back button or the front button, that's using stacks. Or maybe you're writing a piece of text and you want to undo something, so you can click the undo option to go back, or forward to redo. Ever wonder how that works? Well, the idea comes from stacks. That is, you store the previous state of your work in the memory in such an order that the last one appears first. This is something that we can do with stacks. As you can see over here, stacks usually come with 3 types of methods. There's a few others, but these are the main ones. Pop, push, and peek. Pop is remove the last item, that is, remove the plate. Push is add a plate. And peek is simply view the topmost plate. I've added lookup in here just to show you that it's big O of n, because you usually don't want to traverse through an entire stack. But just so you know, if we wanted to do that, it's going to be a heavy operation. Let's talk about queues in the next video. Bye-bye. Welcome back. Queues are our next data structure. And the best way to think about them is like an entrance to a roller coaster. The first person that arrives in line gets to go first on the roller coaster. And then the second person gets to go, and then the third person gets to go. Then the fourth, the fifth, and the sixth finally gets to go. So it's the opposite of stacks in that we access first in, first out. The first item in the queue gets access first, that is first out. We call that FIFO. And queues are used, again, a lot in programming problems and interview questions. For example, if you had any sort of waitlist app to perhaps buy tickets for a concert, that uses queues. What about a restaurant app where you check into the restaurant to see if you can get a table? That uses queues. What about Uber or Lyft when you want to grab a ride? Well, the person that requested the ride first will get priority, and then you'll get second. And then finally, the most common example of queues is a printer, right? If you had a printer at home and you had 3 people on 3 different computers at your home, let's say your family members, and you press print and each person prints different items, the person that clicks print first should have their first printout. And same for the second person that goes next, and then the third person. Now, on the right here, I have a couple of words that are different than push and pop. And I'm using a bit of standard here. You can use push for enqueue, which means add to the queue, that is add a person in line, which is O1, and dequeue, which you can think of as pop, which is remove person from line. However, dequeue, unlike pop, doesn't take the last person in line, it takes the first person. So that's where stacks and queues differ, and we have these names to make sure that we understand the differences. But we have peek, which once again tells us what's the first item that's going to come out. That is the first person in the list versus a queue that is the last plate, which was the last in, first out. And once again, lookup in a queue you usually don't do because you're only interested in enqueuing and dequeuing. You can see here that our big O notation is quite fast. We're actually going to demonstrate this in code, but I want you to try and answer this question. Why would you not want to use an array to build a queue? Pause the video if you want to think about it. Well, the answer is that it's very inefficient because we're removing the first item from the list. If you remember, arrays, if you unshift something, you remove the first item, you're going to have to shift all those indexes. So creating a queue from arrays, although you can do it, is really, really bad. And that's something we'll talk a little bit more about when we actually code it. Okay, that's enough for queues. Let's go on to our first exercise. Welcome back. Let's do a quick exercise before we actually create our own stacks and queues because JavaScript doesn't have its own stack or queues data structure. Now, I mentioned that there's 2 ways that we can build stacks and queues. If we talk about stacks, we can think of it as our browser history. Let's say we visit Google first, then we visit udemy.com, and then we visit, let's say, YouTube. In a stack, because Google was the first item, it would actually be placed on the stack like this. Then we go to Udemy, so we'd be placed on the stack on top, and then we go to YouTube. Now, if we want to go to a new website, let's say we go to Twitter, but then we decided, no, that's not what I wanted to do. I want to go back. Well, we remove Twitter, press back button on our browser, and we get to YouTube. If we press back again, we get to Udemy, and then back again, we go back to Google. So stacks has a top and a bottom, and we can build it with either arrays or linked lists. My question to you is, why would we want to build stacks with arrays? That is, we'll create a class of stacks that has the data being held in arrays versus using linked lists and vice versa. Think about that. What about queues? Let's say we have a queue. I'm creating a waitlist app. And In here, we have a couple of people that want to get on the wait list. The first person that shows up is Tim. And then after Tim, or you know what? Let's use our names. Let's use Matt. And then Matt shows up, but all of a sudden, Joy comes and lines up. And then perhaps we have Samir that comes and waits in line, and then we have Pavel. In this case, we want Matt to be first, then Joy, then Samir, then Pavel. And with queues, we can once again use arrays and linked lists to implement it. Which one do you think would be better for queues? Is there one better, or are they both equal? I want you to think about this. In the next video, I'm going to answer this for you, but I recommend taking time to think about what you know about arrays and linked lists and how they might benefit or might not benefit stacks and queues. I'll see you in the next video. Bye-bye. Welcome back. How did you do in that exercise? Let's have a look at the solution. Let's start off with stacks. I said that with stacks, they can be implemented using arrays or linked lists. In this case, both arrays and linked lists are going to work fairly well. In the end, it depends on what you prefer and what your priorities are. And by this point, you should understand the pros and cons of arrays and pros and cons of linked lists. So we don't need to go into much detail since we've talked about it before. But one major thing is that arrays allow something called cache locality, which makes them technically faster when accessing its items in memory because they're right next to each other, versus a linked list that has them scattered all over memory. And also, linked lists have extra memory associated with them because we have to hold on to those pointers. But on the other hand, they have more dynamic memory, right? And we can keep adding things to the list versus an array where you have either a static array or dynamic array that has a certain amount of memory, and as soon as it's about to reach its limit, it's going to have to double up that memory and create new space for it somewhere in memory. So you have to think about what sort of operations you're going to do and what your priorities are to decide which one you want. But they could both work. And we're going to build a stack data structure with both of these coming up. Queues, on the other hand, is a very simple answer. You would never want to build it with an array. Or if you do, well, that's not necessarily a good idea. And ideally, you want to implement them with linked lists. Why is that? Well, if you remember, arrays have indexes associated with them. So if we had Matt here, then we have Joy, then we have Samir, then we have Pavel that are in queue. If this was in an array data structure and Matt was the first in line and we need to remove Matt from the queue, well, once we remove Matt, we now need to shift the indexes over. So we have to go one by one and say, all right, Joy is now here at index of 0, Samir is at index of 1, and Pavel is at index of 2, and there's nothing at index of 3. We just unshifted those arrays. It's an O of n operation, a linear time. Versus something like a linked list, where all we have is a pointer to the head, and then perhaps we have a pointer to the tail. And all we need to do is say, head, well, is Matt. We want to remove Matt, and Joy is going to be the head, and nothing else changes. And that's an O of 1 operation, or constant time. I hope you are able to get the answer. Otherwise, at least now you know, and this is a very common interview question that you might get asked, that hopefully you have an answer to now. But enough talking. I think it's time for us to build these data structures from the ground up. I'll see you in the next video. Bye-bye. Welcome back. It's time to code our own stack. And I have a little exercise for you here. I've created the template of what we want our stack data structure to look like. And we also have a class of node if you decide to use that, and you should be familiar with it from our linked lists exercise, or you can just ignore it and then create a new node yourself in here. Now, this stack is going to have in its constructor 3 properties. We have the top, which is, remember, the top plate. We have the bottom, which is the bottom plate. And then we have length of 0. And both top and bottom are currently null. Now, we're going to be using linked lists to fill these values. But we don't need to use the linked list class that we've used before. Instead, you can just use the node class to simply assign different values and make sure that the .next points to a different node as we add things. Now, your task is to create 3 methods that work for this data structure. Peek, which lets us see the very top element or top node. The push, which lets us add a node to the top of the stack. And a pop, which lets us remove from the top of the stack. And if you want, optionally, you can also do an isEmpty method, which is common with a stack, to check that our stack is empty. We'll start off with a myStack that gets instantiated. And your code works if you can do something like this, where you say myStack.push, let's say Google, then push Udemy, push Discord, just like a browser history. And then you can pop Discord, then pop Udemy, pop Google. Good luck, and I'll see you in the solution video. Bye-bye. Welcome back. Let's have a look at how we would want to solve this question. That is, how do we create a stack data structure that has peek, push, and pop? Now, peek should be fairly easy, right? We just want to see the very top item on the stack. So I can just say peek is going to return this dot top. That's it, nice and simple. So that if we run myStack.peek, it's going to return null because, well, there's nothing in our stack. This dot top is null. That is empty. Let's go to the interesting one, that is push. How do we add things to the stack? Well, the very first thing we want to do is to create a new node. And like I said, we can create a new object here if we want, or we can just use the node class that I provided for you here. We can use the class by saying new node, which instantiates the class and gives it the value that we're going to push with. Next, we want to check if this is the very first item, because if the stack is empty and this is the very first item, well, top and bottom are both going to point to the same node. So in that case, we can check for if this.length is equal to 0. In that case, we can just say this.top is going to equal the new node. And also this.bottom is going to equal the new node. Otherwise, we have to do something a little bit different. But not that different because we've seen it in the linked list example. We just have to change some pointers around. In our case, we want to say const holding pointer to the very top node, because whatever on top now is going to get replaced by whatever we're going to add to it. So we're going to hold the reference to what was top originally. And then we're going to say that this.top is now going to equal the new node. And this.top.next, which is now the new node, is going to point to what was top beforehand, but now is below it. So we just say holding pointer, so that is the old top, is now going to be right after our new node. And then finally, we do the this.length plus plus to increment the length by 1. And then finally, we want to return, let's just return this, which will return us the linked list. Let's see if that worked. I'm going to say peek first. Well, there's nothing here. But if I want to push to my stack, I'm going to say push, and we'll push Google first because we're visiting Google first. And if I run this, I get a data structure that has top, that has the node value of Google. Next is null because we only have one item. And the bottom is also the same Google with next null. And our stack has a length of 1. What if we keep adding here? Let's go to Udemy next. If I click run, I now have a length of 2 stack that has top node as Udemy and bottom node as Google. Because remember, with a stack, we stack plates on top. That is, Udemy came in last, so Udemy is on top. Remember LIFO, last in, first out. Let's add one more. Let's say that we next visit our Discord community. So let's say push Discord. And I click run. And there you go. We have our Discord community at the top. At the bottom is node. And just to make sure that our peek is working, if I do peek, we should get Discord because it was the last in and the very top of our stack. Very nice. I hope you got that. Let's continue with pop, that is to remove whatever's on the top of the stack. Well, let's first check to make sure that there is an item, because if there isn't, and we just have null, well, we just return null. So in this case, we can just say if this.top, if it doesn't exist, in that case, we'll just return null. Then next, we can just do our const holding pointer to this.top. So what is currently at the top, which is Discord. And we'll say that this.top is no longer what it currently is because we want to remove it. It's going to equal this.top.next, which is underneath Discord. And then finally, we say this.length minus minus because we want to decrease the length by 1. And then finally, we can say return this. Now, remember, because JavaScript is a garbage collected language, if I didn't do this and said holding pointer to this.top, well, Discord, this node that contains Discord, wouldn't be referenced by anything and not used by anything, which means in a garbage collected language like JavaScript that it will get automatically removed from memory during garbage collection. So if I run this, well, I haven't done anything yet, but right now for pop, let's just return the holding pointer. If I click run, or let's first do my stack.pop to remove Discord from the list. If I click run, I get back the Discord node, which is the holding pointer, in case we still want to have access to it. Otherwise, if we just want it to disappear and we don't need it anymore, we can just return this. We can even comment out the holding pointer. And if I click run, we now have just Udemy at the top and Google at the bottom. And Discord is disappeared from memory. So let's keep going here. Let's say I want to pop one more. And if I run this, I now only have one thing, the Google, which was original item on the stack. So what we just did was we went to Google, then we went to Udemy, then we went to Discord. And then we popped whatever's on the top, and then we popped Udemy, and now we're just left with Google. If I do one last pop here, and I click run, we have top, which is null, but we have bottom node still having Google because we never removed in the pop our bottom node. All we did was replace the top. So we just need to add one conditional here, which is if this.top equals this.bottom, that means there's only one item on the list. I could have also done this.length equals 0. If both of them are equal, which means there's just one node left, in that case, we want to say that this.bottom is going to equal null. Because after we remove the only node left, we want bottom to equal null. So if I do this and click run, there you go. We're back to our original empty stack. I hope you got that and were able to make sense of it. We have another exciting exercise in the next video. I'll see you in that one. Bye-bye. Welcome back. We just implemented our own stack. And hopefully you're able to code along as well in your own language. Now here's my next challenge to you. What if we used arrays for this stack? Up until this point, or what we've coded in, has been with a linked list that we've created. How would you change the code if you want to implement this in an array? And the hint here is that it's going to be super, super simple. It's going to involve deleting a lot of this code because, well, arrays already have push and pop. So my challenge to you is to convert this stack data structure to use arrays instead of linked lists. Good luck, and I'll see you in the next video. Bye-bye. Welcome back. Let's convert our stack data structure to use arrays. And this is going to be fairly simple. All we're going to do is remove all of this in the constructor and have this.array equal to an empty array. We don't need the length property because that comes built in with arrays in JavaScript. Obviously, this may be different for different programming languages, but for now, we have this available to us in our language that we're using right now. So there we have it. That's our constructor. What about peak? Well, peak simply means we want to see the very end of the array. Remember, with stacks, it's last in, first out. So when we do a peek, we want to see the very top thing, the latest thing that we've added. In our case, we can just simply say this dot array, and we're going to access that array with bracket notation, and it's going to say this dot array dot length, which is the length of the array, minus 1. Because we do minus 1 because our index starts from 0 to 1 versus the length that starts from 1 to 2. That's it. We have peek implemented. Let's just comment this out and make sure that peek works. If I run this, we get undefined, well, because there's nothing in the array. And we can probably give better errors if we wanted to here, but for now, I think this is fine. What about push? Well, with push, we get to delete all this code and simply say this dot array dot push value. How nice is that? That was nice and clean. Comes pre-built with arrays. We can just use push. So if I do my stack dot push and I click run, well, peek here is giving me Google, but let's just run push only. I get a stack that has an array with Google in it. If I push to Udemy, I've added Udemy. If I do push Discord, I've added Discord. And if I do peek here, I should get Discord back because it's the latest entry. There you go. How simple was that? That means that pop is also going to be very simple, right? Absolutely. Feels good deleting code, doesn't it? What we do is this dot array dot pop. That comes already in JavaScript. We can just return this if we want. If I click run, well, we'll have to run the pop here. Let's run pop, which removes Discord from the list. If I run pop again, I get Google. And if I pop this and I click run, we have an empty array. Look at that. Nice and simple. We don't even have to use the node class, and that's pretty nice, right? So you can just use arrays as stacks quite easily. And we've already discussed the pros and cons in using linked lists versus arrays. One of the nice things about using an array is, well, arrays, at least in JavaScript, already act like stacks, and it makes things very simple for us. But enough about stacks. Let's implement our own queue this time around. I'll see you in the next one. Bye-bye. It's time for another exercise. We've learned how to create a stack data structure, but what about a queue data structure? Luckily for us, a lot of the principles are going to be the same. And if you are able to understand how the stack data structure works, then you should have no problem building a queue data structure. I've created a template to start us off here, and your job is to create these 3 methods. Peek, which we're familiar with. We want to peek and get the very first item in our queue, or our line, as I like to call it. And in our constructor, instead of having top and bottom, like we did with a stack, we have first and last. Who's first in line, who's last in line. And obviously a length of 0. And your job is to create and fill out these methods. OnQueue, remember, is to add to the queue, and DQ is to remove from the queue. Remember that the difference between a stack that uses pop is that DQ removes from the front of the list, whatever is first. And again, if you want, you can create another method called isEmpty. And your goal is to create this queue so that you can create a waitlist app where Joy gets in line, then Matt gets in line, then Pavel gets in line, then Samir gets in line, and then you're dequeuing them one by one with first come, first serve basis. Good luck, and I'll see you in the solution video. Let's implement our queue data structure. The very first thing we're going to do is the nice and simple peek, which simply tells us what is the very first item in our queue. So this dot first is what we want to peek into. If I run my queue dot peek, I should get null because, well, there's absolutely nothing in our queue. What about onQueue or enqueue? I'm not sure how to pronounce that. Let's go with enqueue. In there, we want to add to our waitlist. Again, similar to what we did with stacks, we're going to create a new node, and we're going to instantiate this new node with a value. Remember, we have the class here. And this value is going to get added to a node that has this dot value and this dot next. We then want to check and say, hey, if this dot length is equal to 0, that means there's nothing in our queue, then simply say this dot first is going to equal the new node. And same with this dot last, because there's only one node in our list. This is very similar to what we implemented in the stack. Otherwise, we can say that this dot last dot next, so that is whatever is at the very last of the line, and whatever the next value is, which initially whatever is last is pointing to null, but we want to update that to say this time, instead of pointing to null, point the new node as the last in line. And we want to update this dot last to now equal the new node. So that whatever was last in line is now pointing to the new node, and the new node is now last, which is going to make sure that this dot last points to null. Finally, we can't forget to increase the length by 1. And then we can just simply return this, our data structure. So let's have a look. We want to create this line, queue. So all we're going to do is say we want to onQueue joy. If I click run, first node, I get joy with next null, and last node is, again, joy with next null and length of 1. So far, so good. What if Matt comes and gets in line as well? If we add Matt, we now have first node that is joy and last node that is Matt. And you can see here that the first node of joy is pointing to the next node that is Matt. All right, let's add a few more. We'll add Pavel, who just got in line, and then finally Samir, a little bit late, but he got in line as well. If I click run, perfect. Our last node is Samir. We have a length of 4, and we have the joy node, which is the very first item in our queue. Now, let's say we open the door and we start letting people in. We want to dequeue this list and go from the very first in, first out, all the way till the end. Once again, it's very similar to a stack, except that we grab the node from the beginning instead of at the end. So we're first going to say if there's no this dot first, if there's no first item, we can also check the length here if we want. So the list is empty. In that case, just return null. And by list, I mean the queue. If the queue is empty, then return null. We also want to check if this is the last node in our queue. So we can do something similar with what we did in stacks. We can say if this dot first equals this dot last. Again, we can just check length here as well if we want. But for now, this should be fine. If that's the case, I want this dot last to equal null. Remember, we make sure that now last points to null. And regardless, as soon as we dequeue, we want to say this dot first equals this dot first dot next. That is, whoever is first now, because we're going to remove joy, we want who's ever after joy, that is Matt, to be in first priority now. And then we simply say this dot length minus minus to decrease the length, and we can return this. If I run this, well, it's the same thing because we haven't run it here. So let's go ahead and do that. Let's first of all run my queue.peak to see who should be coming out of the queue, and that is joy. So if I do my queue.dequeue and I click run, we see that now Matt is first in line, joy has been removed, and length is of 3. And one thing to point out here, once we run dequeue here, we've completely lost the joy node from our memory because we have no more reference to it. Nothing is pointing to that memory space. And JavaScript, the way it works, is going to garbage collect and remove joy. If we wanted to hold a pointer to joy, then we could say const holding pointer and say this dot first, so that before we update whoever is first, we can reference it with this variable so that we could potentially, if we still want to use Joy, for example, in a waiting list app, maybe we still want to do something to the user. We can do this and still have access to the Joy node. All right, let's finish this queue. Let's dequeue everybody from here. If I do dequeue, and let's return this back to this so we see what's happening. If I run, now Pavel is first in line and Samir is last in line. If I click, or if I had dequeue again, and I click run, Samir is the last person on the list, but then we can finally let him in as well. There we go. Now we have an empty queue, and we've just implemented our own queue data structure. Well done. Hope you had fun. I'll see you in the next video. Bye-bye. Welcome back. One of the most common interview questions when it comes to queues and stacks is this one. Implement a queue using stacks. Huh? Yep, you can implement queues using stacks. And it's especially easy if you create a stack using arrays. Now, this question is on LeetCode, which is really, really nice because we're able to see the solutions explained, as well as solutions in different languages. If you go to discuss and type in, let's say, JavaScript, we get solutions that people have submitted. You can see votes as well of the answer of how to do this. If you want to check Python, because let's say you're writing in Python, well, they have that too. Any language you want, you can find here. Now, I have the answer for you as well. And in this video, right around here, in the available resources, you'll see a REPL with my answer on it. But I want to challenge you and pretend you're in an interview to implement queue using stacks. How would you go about doing it? You can actually even code it on the LeetCode website if you want, using whichever language you want. And just a heads up here, if you are using JavaScript, that they use the prototype way of adding methods. But the class syntax that I showed you is the newer version. It's underneath the hood. It's the exact same thing as doing .prototype. However, it just looks cleaner using the class syntax. So that's what we did. So good luck with that. Have fun. And I'll link to the solution code for you right over here. And there we have it. We've learned stacks and queues. And an easy way to remember them is just simply plates and a waiting line. We learned why they're built on top of other data structures like linked lists and arrays. And we also talked about how to build stacks with arrays and linked lists, and also why we might not want to use an array to build queues, and also built a queue data structure with linked lists. We learned that stacks and queues are great for some fast operations that they have, such as removing or inserting, such as at the end of the data structure. We can also access the very first item in a queue or the very top item in a stack. And we also have all our data ordered, which is really, really nice. But we don't usually use our stacks or queues to really do any sort of lookup or search through the data structure. All we're interested in is the end bits of the data structure. So they make it really useful by restricting our use of what we can do when it comes to stacks and queues, but making sure that what we're allowed to do with these data structures are going to be really, really fast. And there we have it. We've continued to expand our mind map of data structures. So we completed our stacks. We learned how to create stacks with arrays and linked lists. We've learned about their big O notation. And we also talked about queues and how we wouldn't really want to use an array for a queue, a very common interview question. We learned how to use a linked list to create a queue. And also we learned about the big O implications, which is very similar to stacks. We're getting closer and closer to filling out this mind map. But before we do that, we still have a few more data structures to go. But the end is almost near. We only have trees and graphs to talk about. For that, I'll see you in the next part. Bye-bye.